We're going to continue to talk about parametric equations today. So I have a few examples. One thing we really didn't talk about is we had more complicated parametric equations. What if you just wanted to write a straight line in parametric equations? Well, we know there's several forms in rectangular. And one of them is if you have a point and a slope, and that's exactly what you need to determine a straight line. We have y minus y0 equals the slope times x minus x0, the point slope form. But in parametric, we have to have x is a function of t and y is a function of t. Well, to make sure that it goes through the point x0, y0, it would be easy just to put those in there. And then, to make sure that it has a slope of m, if we put plus t here and plus mt here, that means for every time t goes up by 1, that's going to make x go up by 1, and y is going to go up by 3 times that much. So that's what it means to have a slope of 3. So this should be a way that you can write any straight line. If you know the point and the slope, you can write the parametric equations. So, a quick example. You've got the point 1, 2, and you want to have it the slope of 3. You would just put 1 for x and 2 for y, plus t, and then plus 3t. And that certainly would be one answer. And if you look at it, if you had t equals 0, you'd be at the point 1, 2. And when t equals 2, you'd be at the point 3, 8. Now, if you wanted to make this go faster, you could still have the same straight line if you went plus 2t and 6t. Because now, at t equals 0, you're at the point 1, 2, and at t equals 1, you're at the point 3, 8. So you can just make the movement go twice as fast. And you can see that dx dt is 1 and dy dt is 3. So you know it's going to be going up. If you wanted to be into the right, and if you wanted to make it go down and to the left, all you would have to do, say from this original one, you could go 1 minus t and 2 minus 3t. And now dx dt would be -1 and dy dt would be -3. So now it would go down and to the left. So those are some things that you can control the movement in parametric equations. Now, what we haven't looked at is what if you don't have x as a function of t and y as a function of t, but you have dx dt and dy dt as functions of t. So this is sort of similar to in rectangular when we know, instead of the function, we know the derivative. So this is similar to having a differential equation. And say we had an initial condition. So we knew at t equals 1, the position of a particle, say this is something moving, was at -3, 0. And you wanted to know at t equals 4, where is that particle going to be? So we need to know something about x and y. So there's two ways you can do this. Similarly, when we did differential equations, we can take the antiderivative. So x would be t cubed over 3 plus c. And we would know that x was at -3 when t was at 1. which would make c equal negative 10/3. So now you could find x to be t cubed over 3 minus 10/3. So if you wanted to know x at time 4, just plug it in, you'd get 64/3 minus 10/3, or 54/3, or 18. So you now know x is over at 18. And you could do the same thing for y. This is t to the 1/2, so it would be t to the 3/2 divided by 3/2, or times 2/3 plus c. And y is 0 when t is 1. So c would be negative 2/3. So y would be 2/3 t to the 3/2 minus 2/3. So at time 4, you'd have 16/3 minus 2/3, or 14/3. So you'd be at 18 and 14/3. And to just kind of check yourself, does that make some sense that we might be going up and to the right? Well, since you have the square root of t here, we can only use positive values of t in our domain. So that means both dx dt and dy dt are both going to be positive, so it is going to be going up and to the right. Now, just showing you one other way you could have done this same thing. You could have said that the old value of x was negative 3, and what determines the new value of x? It's the rate of change of x, or dx dt. So we could just take the integral from time 1 to time 4 of the speed in the x direction times dt. So we get negative 3 plus, and the antiderivative would be t cubed over 3. So you get negative 3 plus 64/3 minus 1/3, or 21. 21 minus 3 is 18. And the same thing for the y value. You could say y was 0, but from time 1 to 4, the rate of change of y times the time is going to give you the new value of y. So dy dt is t to the 3/2 times 2/3. So you get 8 minus 1 is 7, 14/3. And either way is about the same amount of work. The only advantage of this second way is if you didn't know how to take the antiderivatives of these, if they were really complicated, and you did have the use of a graphing calculator, then you could do those integrals on your calculator. So that is some advantage of the second way. Okay, so we have a little more complicated parametric equation here. And the domain is from 0 to 2 pi. So let's get some idea what this looks like. When t is 0, x is 1 and y is 0. At pi over 2, the cosine is 0 and the sine is 1. At pi, the cosine is negative 1, and when you cube it, it's still negative 1, and the sine is 0. And then at 3 pi over 2, you get 0, negative 1, and then you're back to where you started. So that looks kind of similar to what we did before. It kind of looks like it might be a circle. But we're not sure. We don't know what happens in between. So what could we do? We could take derivatives. So this is really the cosine of t cubed. So you get the derivative is 3 times cosine of t squared times the derivative of the cosine, which is minus the sine of t. So altogether you get negative 3 cosine squared of t sine of t. dy dt would be the same thing. It's 3 sine squared of t times cosine of t. And if you hadn't already plotted these points, you can get some idea. Like, we know sine squared is always positive, and 3 is positive. So from 0 to pi over 2, the cosine is positive. So dy dt is positive. You're going to be always going up. Then you go into the second quadrant, and the cosine is negative. You're going to go down. And it's still negative in the third quadrant, so you're going to go down and then up. So we have some idea that it is going the same way we thought when we plotted those points. But what might really be nice is to know something about the concavity. So to get the concavity, then we have to take the second derivative. So first we have to get dy dx. So dy dx is dy dt over dx dt. Negative 3 cosine squared of t sine of t. So 3 divided by negative 3 makes it negative. And you have a sine of t in the numerator and a cosine of t in the denominator. So you get minus the tangent of t. So that becomes our dy dx. So if I want to get d squared y over dx squared, I've got to think of this as the new y. And I'm taking the derivative of that with respect to x. So I have to go dy dt, which is minus secant squared of t, still over the same dx dt, which is minus 3 cosine squared t sine of t. Minus divided by minus is plus, and we see that's positive, and that's positive, so it's the sine of t that's going to determine the concavity. So from 0 to pi, when the sine is positive, it's going to be concave up. So I know from here to here, it's got to be concave up. Concave up. And then when the sine is negative, it has to be concave down. So it isn't a circle. It's an asteroid. So this is the equation of an asteroid in parametrics. And what you might wonder, what would be the most efficient way if you were trying to get around those points? Should you go on the circle or should you go on the asteroid, or doesn't it matter? Well, I think we can find the distance on the circle. The radius is 1, so the circumference would be 2 pi r. So that's the distance it would be if you were going on the circle. To find it on the asteroid, we don't have a geometric formula. So we have to use the length is the integral from 0 to 2 pi of the speed times the time. Well, the speed is the square root of dx dt squared plus dy dt squared. So I have to square this, so I get 9 cosine to the 4th of t sine squared of t plus dy dt squared is 9 sine squared t, or sine to the fourth of t, oops, I ran out of room here, times cosine squared of t dt. And it looks like it's going to be really complicated, but what can we factor out of here? There's a 9, and there's a cosine squared in both places, and there's a sine squared in both places. And when you factor it out, you get cosine squared t plus sine squared of t, which is just 1. So that makes things a little bit better. And the square root of something squared is just going to be 3 times the absolute value of cosine of t times sine of t. Okay, dt. Now, because of the symmetry of the sine and the cosine, we can, and it's going to make our job a lot easier, to just go 4 times and just go in the first quadrant when the sine and the cosine are both positive, so we can drop the absolute value sign. And then we have, if we think of sine of t to be u, we have du. So we can just go 12 times u squared over 2 from 0 to, I'm sorry, we changed that to pi over 2 because we're only going 1/4 of the way. So altogether, you get 12 times 1/2 minus 0, or 6. So it's really close, but you can see 2 pi is around 6.28, so it's a little more efficient to go along the asteroid. Amazing the things you can find when you know parametric equations. Okay, so I have 2 more examples. So here is something we haven't seen quite before, but it is parametric. Let's try some values of t. When t is 0, you get 0, and 1 minus the cosine of 0 would be 0. So you're right here at the origin. When t equals pi, and I'm going to write, sometimes it's nice to write what the time is that you were at these places. You can see the x and y value, but you can't see the t value when you plot it. So it's kind of nice to note that. When t equals pi, you get 2 pi for x, and 1 plus 1 is 2, so you get 4. So you get 2 pi for x and 4 for y. And that's at t equals pi. And then at t equals 2 pi, you're at 4 pi for x, and you're back down to 0. So what happens is, you have that, and that's the beginning of a cycloid. This would just then repeat again. And that has something to do, a cycloid has something to do if you put like a marker on a wheel and then you watch the progress of that as you rolled the wheel. Anyway, what would I want to do with that cycloid? One thing I might want to do is know what the length of it is. What is the distance from here to here? So again, we could do similarly to we did over here. We could take dx dt and dy dt. That seems to always be a good thing to do. So dx dt is 2 times 1 minus the cosine of t, and dy dt is 2 times 0 minus a negative sine of t. So 2 sine of t. And before we find the length, let's just see if everything seems to make sense. Since the cosine of t never gets bigger than 1, dx dt is always going to be positive or 0. So you're always moving to the right. And dy dt, since it's the sine of t, from 0 to pi, dy dt is positive. You're going up and then you're going down. And say they asked you, when is it stopped? Is it stopped at this point and this point? Well, at time 0, dx dt is 0 and dy dt is 0. So it's stopped here. And the same thing at 4 pi. Well, I mean, at t equals 2 pi. I didn't write that down. X is equal to 4 pi, but t is 2 pi. So dx dt and dy dt would both be 0 here, so it would be stopped. But is it stopped up here? Well, if you put pi in here, then you get 1. So dx dt is still positive. It's still moving to the right. It's just dy dt that's negative. It was going up and now it's going down. So it's stopped in the y direction but not in the x direction. It's just progressing there. So if you ever want to know if it's stopped, you have to look for both of them. Okay, so let's find out what the length of this is. It's the integral from 0 to 2 pi, that's the time, the square root of dx dt squared, so that's 4 times 1 minus the cosine of t squared, plus dy dt squared, which is 4 sine squared t dt. Now, can we simplify this? First of all, we could bring out a 4. And the square root of 4 is 2. And then we get the square root of 1 minus 2 cosine of t plus cosine squared of t. And then you have plus sine squared of t. So cosine squared plus sine squared is 1. So this just becomes 2 minus 2 cosine of t under the radical dt. And at first thought, you're kind of stuck. But we've got this formula that says sine squared of t equals 1 minus the cosine of 2t over 2. So if I just plugged in place of t, if I plugged in t over 2, I get 1 minus the cosine of t over 2. And if I multiplied both sides by 4, then I get 2 minus 2 cosine of t. I know that's a little bit tricky, but now you have the square root of, instead of this, you can call it 4 sine squared of t over 2. And the square root of 4 is 2. And if you have the square root of something squared, it's the absolute value of the sine of t over 2 dt. But again, since you're going from 0 to 2 pi, the angle here will never be bigger than pi. So what's inside absolute value is positive, we don't really need to consider the absolute value. So what's the antiderivative of the sine of t over 2? It's minus the cosine of t over 2 divided by 1/2 or times 2. So you get negative 8 times the cosine of pi minus the cosine of 0. That total distance is 16 along that cycloid. So you do see it goes up quite a bit, because from here to here is only about 12 point something, because it's 4 pi. So it is more efficient, obviously, to go here than like this. Okay, so one thing I haven't talked about is you can do things like volumes of revolution and areas. So we've got another parametric equation here. Well, you're from 0 to the square root of 5 is our domain. If we were trying to graph it, we know we're at 0, 0 at time 0, and at the square root of 5, you'd be at 25/2 2 root 5. I'm sorry, 5/2 2 root 5. Now, another thing that we maybe have only done once, you can always change these into rectangular. Also, if you want to get an idea what something looks like. So I could say, solving in here, that t equals y over 2, so x is y over 2 squared over 2, or x equals 1/8 y squared. So you can see that this is a sideways parabola. So it's going to go like this. You kind of knew that it was going up because dx dt is t, and dy dt is 2. So it's always going to the right, and it's going up. But say we took this now, and we wanted to find the area, or the volume of revolution. We can do this very much like we did it before. So let's do two things. Let's first take this right in here and revolve it around the x-axis and find volume. So what I can do, I don't have to find something new, a new formula. I can just do it the way I did in rectangular. I can say the volume, since it's right up against that axis, we can do it with disks. So I can go pi times the integral from x equals 0 to x equals 5/2 of the height squared, the radius squared, the height, y is the radius, dx. The trouble is, we have y as a function of t. Now you could turn everything into rectangular, but let's not. Let's do this all in parametric. So what we have to do is change everything into t. Well, y is already in terms of t. It's 2t squared, and we know the time is from 0 to the square root of 5. And what do we do about dx? Well, we know right up here that dx is t dt. dx dt is t, so if you did it as a differential, dx is t dt. So now we've completely switched this over in terms of t. So altogether, what do we have? 4t cubed. I can bring the 4 here. So you get t to the 4th over 4. So you get pi times the square root of 5 to the 4th power is 25. So 25 pi cubic units would be the volume. So let's just end this up with taking that same volume of revolution and trying to find the surface area. This isn't even a required topic, but it still shows you what you can do. And I want you to understand, even though this is not a required topic, that finding surface area is possible of one of these volumes of revolution. So to think about it, what you've got is still this rectangle, except it's not quite a rectangle. What you have is this little distance right up here, and it's square down there. So if I want to get the surface area, I'm going to take that rectangle and revolve it around, and I'm going to get the circumference of that circle, and then I have to multiply it by that little distance right there to turn it into surface area. So what we consider this is this distance right here is dx, and this is dy. So right up here, that's going to be the square root of dx squared plus dy squared. So to get the surface area, we would go the integral, and let's do this right in terms of x first. The circumference is 2 pi r, and r would again be y, but then times this, which is the square root of dx squared plus dy squared. And it's going from x equals 0 to 5 halves. But again, let's turn this into the variable t. So we can bring the 2 pi out front, and t is going from 0 to the square root of 5. Y is 2t. Now, what are we going to do with this? Well, in any case, we don't have a dt. So what we could do is divide by dt squared underneath the radical and then multiply by dt. So you have the square root of dx dt squared plus dy dt squared dt. And now we've got it completely shifted over. And if you think of this as t squared plus 4 to the 1/2 power, I think it's in kind of a nice shape. We have u to the 1/2, and 2t dt is du. So we can take the antiderivative, would be u to the 3/2, so t squared plus 4 to the 3/2 times 2/3. So altogether you get 4 pi over 3. And if you put in, that's the square root of 5, you get 9 to the 3/2, which is 27, minus 4 to the 3/2 was 8, So you get 19 times 4 pi over 3. 76 pi over 3, and they would be in square units because that's surface area. So again, I want to emphasize, I didn't want to end this year without showing you that in calculus we can also find the surface area of these volumes of revolutions. Don't worry too much if you didn't understand completely how I found the surface area formula. Anyway, I think we're getting a little bit better at parametrics. Maybe we'll do one more day tomorrow, and then we'll go on to a new way of representing things.